In this video, we are going to discuss a topic that's led to more whiteboard arguments than maybe any of the other topics I teach in biochemistry during, let's say, office hours. So it's a really important concept in metabolic control, but it's also a little bit non-intuitive. And so the question we're going to be asking ourselves is, does an enzyme alter the free energy of a reaction? Now, you probably think, I know the answer to that, or maybe you think, I know the answer to that. It's obvious. But even if you think it's obvious, I think it's worth continuing in this video because there's some interesting things that happen once we start putting an enzyme into the context of a cell. Okay, so very high level review. Enzymes speed up reactions by lowering the transition state. There's some wacky, strange state in the middle here, some configuration of bonds and atoms that's improbable. Enzymes stabilize that, make it more probable, and thus increase the rate that the reaction happens. And what this means is that we can think about how adding an enzyme to a reaction will change the sort of rate and the outcome of reaction. And so let's think about a real biological reaction here. So this is glucose 6-phosphate going to fructose 6-phosphate. This is a reaction in the pathway glycolysis. It has a delta G naught prime that's very close to 0. And in fact, we're going to approximate this for the rest of this exercise as 0. What that means is there's no intrinsic favorability one way or the other for G6P or F6P, that at equilibrium, we will see an equal amount of G6P and F6P. So then we can imagine a set of reactions where we make up a test tube that has a bunch of G6P and less F6P. So we have an excess of reactants. We can then make another test tube that has this one over here. It's got an excess of F6P, so an excess of products. And then we make up a test tube that has both at the same concentration. We then add an enzyme and watch what happens. And what's going to happen? Where is this reaction going to end up? So so maybe pause and think about that if it isn't immediately obvious. So where are we going to end up? Okay, what do I think? Well, I think we're going to end up here. We started with an excess of reactants. We're going to equalize. We're going to end up with the same products and reactants on both sides. Here, we start with an excess of products. So we're going to gain some reactants. They're going to equalize. And finally here, if we started them equal, they're going to end up equal. And we added an enzyme to make this go faster, but actually adding it or not adding an enzyme would have had no effect, right? This is still going to equilibrate to the same position. It's always going to end up at the equilibrium position. So the enzyme is not changing the rate or the direction of this reaction. And so very clearly, it's really important to keep in mind that an enzyme increases the rate of a reaction, but does not change the reaction direction. It will never make a reaction that is favorable, unfavorable, or a reaction that is unfavorable, favorable. You might be saying, okay, so what that means is an enzyme can't change the delta G of a reaction, right? Maybe that's the obvious outcome there. Delta G is something that enzymes don't change. But let's think about it a little bit more. Another way to say what I just said with this is that if a reaction is out of equilibrium, enzymes will start bringing it closer to equilibrium. And if an enzyme is bringing something closer to equilibrium, it's actually changing the free energy of that reaction over time, right? So if our delta G starts out less than 0, and then we add an enzyme, the delta G is going to go to 0. And if that rate would have been so slow we would have seen it without the enzyme, then really the enzyme is actually causing a change, at least in the observed free energy. It's causing the reaction to equilibrate more quickly. So we can put that on a graph like this. Let's imagine we start with a delta G that's very negative. So we've got excess reactants. That's how we're going to start. And what we're going to see over time is this reaction, say without an enzyme, no enzyme, is going to eventually equilibrate to something up here where this is at equilibrium, right? We might have to wait 1,000,000 years, who knows how slow this reaction is, but if we wait long enough, the reaction will equilibrate to the delta G equals 0. We now add an enzyme to this reaction and we observe this curve. So there's our plus enzyme curve. So it much more rapidly reaches equilibrium than it otherwise would. But let's do a thought experiment. Let's say that we make a measurement here. We say, what is the delta G at time t? We would say, the enzyme and the no enzyme curves are different. We're seeing a difference in their delta G just because we added an enzyme to the system. Now you might be saying, okay, semantic detail, who cares? Why does this matter? Turns out that it matters because cells are not at equilibrium, right? We've talked about how cells are continuously running reactions. They're taking in sugar and they're spitting out carbon dioxide, for example. And they're taking oxygen, they're spitting out water. This whole thing has matter and energy flowing through it continually, and it is not at equilibrium. Cells are always equilibrating without reaching equilibrium because they're always throwing more stuff in. They have a source of material that's flowing to a sink. What that means is when we're thinking about an enzyme in a cell, we should actually be thinking about something more like this scenario where the system is equilibrating somewhere rather than some static endpoint where we're asking, what did the enzyme do to the overall reaction? We're actually asking, how does it cause it to equilibrate quickly? Or how does it cause it to equilibrate more or less quickly? So let's actually illustrate this with a physical example. What we're going to be thinking about is a highway with 4 lanes where cars are going from left to right. In the middle, we have a city, and we're going to think about it. Everything to the left of the city is a reactant, and everything to the right of the city is a product. And cars are going to be driving from reactant to product. We're going to ask, how does changing the rate of car flow change what we observe in the reactant and the product category? So let's imagine we take a snapshot from a drone and we see the following pattern. We see, oh my goodness, this must be an Oregon highway in the summer. And we get these nice months of weather. So this is the time to do all the highway maintenance. Of course, this is also when everybody's driving on the road. So a bunch of cars are backed up, stuck here. Pink things are cars, unable to proceed because they all have to fight their way down to one lane. And then we got one car over here that's free and clear and finally zipping off. We can ask, all right, what's the free energy of the cars? And I'm putting air quotes around the free energy because to do this really properly, we'd have to think about forward directions and backwards reactions, all kinds of, a little bit of complexity, not all kinds of complexity, but we have to think about some complexity I don't want to think about for this video. So the intuition is going to hold even if we just think about going from left to right here. But we're going to ask ourselves, what is the free energy of the cars? And to do that, we are going to use our equation down here, the free energy equals delta G naught prime plus RT log of products over reactants. Our delta G naught prime measures the intrinsic favorability of the reaction, right? Do we expect to see more cars on the left or the right? And intrinsically, I don't think we have any preference, right? We'd expect to see them equally on both sides, all else being equal. So our delta G naught prime is 0. What about our RT log of products over reactants? Well, remember, our product reactant line is right there. And so we would say, well, how many products do we have? We have 1. How many reactants do we have? We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We've got 11 reactants. We can look at this and we say, oh, RT log of products of reactants, this number is less than 0. So this is going to be a negative number with a log. And indeed, if we plug those in, what we get is that we currently have a free energy of minus 5.9 kilojoules per mole, assuming our cars are at, 298 Kelvin, whatever exactly that would mean. But overall, what this delta G is saying is that we have an excess of reactants, right? There's more cars over here than there are over here. And the reason there are more cars over there is because it's so slow to go through this closure, right? We've got all these closed lanes, so it just takes a long time for it to cross through this barrier. Okay. What if we open up a lane of traffic? So now there's traffic that's clear. So now we have 2 more lanes open. And what we would see in that case is we would see more cars on the right than what we had before. So now we've got 1, 2, 3, 4 on the reactant side. And 1, 2, 3, 4, 5, 6, 7, 8 on the, 8 on the reactant side, 4 on the product side. You plug in those numbers and you get, well, now our delta G is minus 1.7 kilojoules per mole. Our delta G has gotten closer to 0 because we're seeing an equalization across the left and the right of this highway. Imagine we open another lane. So now we have, 3 lanes that are open. Now what we see is there's only 1, 2, 3, 4, 5 on the product side and 7 on the reactant side, which gives us a delta G of minus 0.8 kilojoules per mole. And lastly, we open all the lanes and now we've got delta G of 0, we've got 6 on the left and 6 on the right. So what we're seeing here is the rate of reaction. In a system where stuff is continuously coming in and continuously flowing out, like a cell where mass is coming in, where molecules are coming in and going out the other side, the rate of an internal reaction crossing this city line sets the free energy of the reaction. That if the reaction is slower, we're further from equilibrium. So slower reaction, further from equilibrium. The faster we make it, the closer we get to a delta G of 0, the slower we make it, the further we are, because there's going to be stuff backing up on the reactant side. What that means is when we look at a system with molecules and energy flowing through it, whether it be cars that are backing up on a highway or cells where molecules are flowing into it, we can make a graph of reaction speed on this axis. How quickly is that reaction able to do things? Versus distance from equilibrium on this axis. The very fastest reactions are at equilibrium, right? Because as soon as a molecule comes in, it equilibrates because that reaction is very fast. There's no limit to the cars driving past the city because all the lanes are open. But the slowest reactions end up being far from equilibrium. And the reason for that is, stuff keeps coming in and there's a finite rate that can come out the backside. And so you end up piling up. You pile up, in this case, you're piling up reactants. That's an up, believe it or not. You pile up reactants, meaning that the reaction is far from equilibrium if it's slow. Now, this, it turns out, is really, really important once we start thinking about metabolic control. Because as soon as you start reading about metabolic pathways, you'll start seeing biochemistry textbooks, the internet say something like, oh, this has a delta G less than 0. That means it's a step that's good for controlling a pathway. And so people usually put it in terms of delta G. They'll say that delta G is less than 0, therefore good for control. And that's true, but I think it's actually more important to say the slower the reaction, the better it is for control. A consequence of the slower reaction is the delta G being less than 0, being out of equilibrium. But the slower the reaction, the better it is for control. And why is that? Because the slower the reaction, a reaction that is far from equilibrium tends to be a rate limiting step. So if you want to control the whole rate of a pathway, all the steps in the pathway, you have to find the slowest step, and that's how you're going to be able to tune the rate. If you increase the rate of the rate limiting step, the whole pathway gets faster, right? If you decrease the rate of the rate limiting step, the whole pathway gets slower. And it turns out the reactions where the delta G is less than 0 are in fact the reactions that are the slowest because they're the ones that aren't equilibrating. They're the ones where they've got 3 lanes closed and all the cars are backing up. So a reaction that is slow is a reaction with a delta G that is not 0, that is out of equilibrium. And because of that, that rate is a rate limiting step where you can control the rate of the entire metabolic pathway. Okay, so what have I said here? I've said that enzymes do not change which direction a reaction will flow. They will not make a reaction that is favorable, unfavorable, or unfavorable, favorable. All that an enzyme is going to do is they're going to change the rate of equilibration. They're going to make a reaction equilibrate more quickly to its equilibrium state. But when you think about enzymes causing changes in the rate of equilibration inside of a cell, what that means is actually the speed of an enzyme sets how far each reaction is from equilibrium. The faster a reaction, the closer that reaction will be to equilibrium. The slower reaction, the further that reaction will be from equilibrium. Making myself go away. And finally, what that means is the slower the reaction, the more useful it's going to be for metabolic control because that reaction is going to probably be a rate-limiting step on the entire pathway. Okay, so hopefully that was useful for you as you're thinking about about enzymes in the context of cells. Big takeaway here is cells are not at equilibrium, and the rate of a reaction in a cell determines how far that reaction in the cell is from equilibrium. So enzymes don't change the favorability of a reaction, but they can certainly change in the context of a cell the actual free energy that we observe for a given reaction by setting how far out of equilibrium it is under steady state conditions. So, okay, that's all for now. I will see you later.